Okay, so countable sets, and I wanna spend a little bit more time on countable sets because there is one interesting countable set that I skipped. Unfortunately, that is the rationals. Okay, so once again, the main finite sets beyond those bigger sets are infinite, and specifically we choose the as a kind of a simple set, not a simple set for countable for this class of sets is the integers. Okay, so for the finite sets, this is it. So you have infinitely many finite sets for each set. All right, for each set there are infinitely many sets of one element, infinitely many of one element, but you can also think of them as these sampled. You can always match them back to these very simple sets. Okay. So you have 4 elements, so you take just 1, 2, 3, 4. That's the set which is you establish a bijection with anytime you want. So now if we go with infinite sets beyond finite, the first simplest infinite set is the integers. Okay, and then it has some subsets that are interesting, and we establish the equivalence or equipotence, if you like, of the integers with the even numbers as well as odd numbers, and then furthermore over here numbers divisible by 3 or divisible remainder of divisible by 3 by 1, and you can think all of those as all countable sets. It is helpful, I think, also to clarify why these work out. We did specify on the right those bijections. But you can actually, if it is a function and it is defined on the subsets of the reals, then why not have a graph? A graph is a very simple graph, right, for this one. So the x's are not really, we are not talking about reals anymore, but you can think about, so from, let's say, from the even numbers, so I'm skipping 1, 0, 2, 4. And then to the reals, okay, the function is x over 2, so it's really not complicated. It will look like this. Okay, 1, 2, 3, 4. Okay, so this is the graph of the bijection we have specified. You can, once again, as we did before, you can verify that it is one-to-one onto. Okay, so it's defined only on integers, on even numbers. It produces all possible integers, and it is one-to-one onto all of that. Okay, so this is x over 3. You can imagine that this x over 3, it will be also take a graph of with slope 1/3, and then once again skip all the numbers but the integers, and so it will be just a bunch of points on that line. Okay. The example that we started with, the equivalence over here between the odd and even, it is, as you can see, a slope is 1. Okay, so all of these examples are quite applicable. One set, however, it is way more interesting, and that is x is the rationals. The rationals. So, well, you know how many rationals. It's not just there are many of them, you know, but they're, well, they're really, the word that we use is dense. They're dense. They're unlike the integers that go like this with gaps. There are no gaps of rational numbers.
No gaps?
What?
There's no gaps?
There are no gaps. That's right. So, well, suppose I take 2 rational numbers, x and y. No matter how close they are, I could find another one, rational number between them. How?
Decimals.
No, what? Take the average. X plus y over 2 will lie between them, and it will be rational. That's what we mean by dense. So there are literally no gaps. So, and then once you find x and y, and then find between them, you can find, once again, take these together, find halfway between them, also rational numbers, and you can, no matter what interval you pick, you'll have narrowing down a sequence of numbers, something that you saw in in calculus. In calculus, and in fact, think about decimal representation of real numbers. Okay, so real numbers you remember, not numbers that are not rational. Okay, but a rational number then will have infinite decimal representation. But if you truncate it, it is rational, right? So finite decimal representation is a rational number, and as you extend it, what do you have? You have a sequence of rational numbers. So if x an irrational number, say is equal to 0.3571011, so whatever that sequence is, if you truncate it, so then this will be x1, this will be x2, and so on. You have x3. That sequence will converge to x. And these are rational, and this is irrational. Okay, remember calculus 3?
I mean,
Calculus 3?
yeah.
I'm sorry, calculus 2. Yes, thank you. So, so sequences, and that is the one of the most prominent examples of sequences. How your decimal representations converge to the number that they represent. That number might be rational, but every finite decimal representation is rational. So as you can see, that's how many rational numbers we've got. Not only you can have them more and more of them as you dense on the numbers, you can every irrational numbers will have a sequence converging to it. So all of this I'm mentioning only to make the point that why it is so important and counterintuitive possibly to say that in fact they are countable. So there are as many rational numbers as there are integers, even though these integers are sparse and these are dense. So the proof is interesting. So the theorem. The cardinality is the same, and so the answer is how. The answer is always the same. We need a bijection. From Z to Q. So don't expect anything as simple as this. So in no specific formula, well actually you might think of a specific formula eventually once the idea is clear, but nothing simple. So let's try to figure out what it could be, and as always with something complicated, you will have to go back to the definition. So, and just on the first day of classes, we actually looked at the definition of a rational number, so we have to do it again. So x belongs to Q if x is equal to P over Q, P and Q are integers. See how we already made a step towards Z. Q not equal to 0. Okay, so as you can see, the rational numbers are simply pairs of integers. So in that sense, if you think about it, remember we had that idea that the Z is twice as large as the number of even numbers, because they're even and they're odd and they're exactly the same number. So if you split integers in half, you'll have twice. It is twice as large as those two sets. This is similar, except we're talking about pairs, so it's like a square. So this, you can argue that that the size of the rationals is the square of the size of the integers. So Q is the set of all pairs of integers. Well, you can add a caveat here is that you don't want to count twice the integers when two fractions when they're reducible. So integers that are relatively prime. So you don't want to count twice 4 over 2 and 2, right? So relatively prime integers and denominator not equal to 0.
What's relatively prime mean?
Means that they have no common factors other than 1.
Is this all pairs of integer because Q is, for X to be a member of Q, it has to be P over Q.
Yeah.
For both P, Q, or Z, so for everything.
Yep.
So what's the difference between relatively prime and prime?
Now prime is a number, it is a characteristic of one number. Relatively prime, they are relative to each other prime, so they don't have to be prime. So once again,
To each other.
right, 9 and 6
Okay.
are not
Yeah,
relatively
yeah.
prime. So every prime number is relatively prime to some numbers but not others. So 3 is relatively prime, but it's not relatively prime with 6 because they have a common factor 3.
Wait, but doesn't 9 and 6 have a common factor of 3?
That's right, so they're not relatively prime.
Oh, okay.
These are
Got
two
it.
examples of
Yeah,
not
yeah,
relatively
yeah.
prime. Relatively prime would be 9 and 25, for example.
Okay.
25, okay, yeah.
So the only point is here is that you want to be able to, you don't want to deal twice with fractions that are reducible. So you want to have only reducible fractions, and what are reducible fractions, if not the fractions with relatively prime numerator and denominator. Okay, so then as I said, then this is where the idea comes from. Then once you realize that you're talking about pairs, and you're talking about how do you arrange pairs? How do you arrange pairs when you're talking about pairs of numbers are plane? So you put p's here and you put q's there, right? So then not every, but a lot of these points will be, in fact, let's just as an illustration, drop out those that do not represent proper fractions. Okay, so I'm plotting here pairs of x and y. So run x, p's run between -2 and 2, and so far q's run between -2 and 3. Okay, so let's just start with these, but it covers the whole plane. Just to make that point about relatively prime and denominator not equal to 0, so let's drop those that we don't want to count. So let's start with q cannot be equal to 0. So I will dropping out these. So these are not part of it because they're not supposed to divide by 0. Not a big deal, but still. Okay, and then let's go. So it's p over q. So can you suggest any one that we should drop?
The 2, 2, 1?
2, 2. That's right. We drop 2, 2
Let's go.
because it's the same as 1. Same as 1. How about -2, 2?
Yeah, of course.
Yeah. So what else? 4 and 2. I don't have a 4 and 2. Well, I think these will also drop. 2, -2. They also have common factors. I think that's it probably. In this little square, we're dropping some of them off. Okay. So all right. So where is the proof? The plan of the proof is. So finding a bijection is just a fancy way of putting something that might sound more familiar. We try to cover the whole Q on the plane with a sequence.
Oh, should you have marked out the vertical axis instead of the horizontal?
What? No, q is equal to 0 is the p-axis. That's where q is equal to 0. So that's why you're dropping them off. Okay. So some of them will be missing, some are not. So that's where the idea of the proof should come from. We have to, and the word countable is very convenient because you literally want to go through counting those points, those orange points. I want to go through all of them in a sequence without skipping. Anybody has ever seen this proof? It's one of those smart ones, but but you can guess. So in other words, you have to come up with a scheme to cover all, to pass through all of these dots, orange dots, or orange. You can even throw out the green ones, or not throw out the green ones. If we cover the green ones too, that's okay. So that's fine. It will be still countable. So let's make our life easier, and let's just think in terms of sequence of just points. So can you think of a scheme for us to cover all of these? You cannot notice that you cannot go row by row because you cannot reach the end of the row. Same with columns. So if it's not row by row and not column by column, what can you think of?
Inside to the outside?
What?
Like inside to outside?
Yeah, that's pretty much it. A spiral. So you don't have to go in that direction or the other direction. You go in spiral of fashion, out, out, out. It would be around the spiral necessarily, but it's easier to just go, like maybe like this, in a squarely fashion. Oops, skip. Like this. Like this, and on and on. The spiral will cover every volume. Okay. So there might be a description of the formula might be more. It might be possible. So the picture is certainly speaks volumes here. The idea is right there. And it is possible probably to come up with a formula, but it might take some work. So we'll just say, well, this is the argument that provides that bijection. So we have covered all the integers, all rational numbers with a sequence of numbers. Okay, so this is but by the way, implicitly we encountered the problem of another example that I did not address, and that is if natural numbers versus integers. Rational numbers versus integers. Once again, same number. Natural numbers and integers. So that natural numbers are starting from 0 into infinity, and z goes back both ways. What's the bijection? It's certainly the problem is easier than we just solved, right? So because we have a and you probably can guess what the answer is. So these are my integers. So go to infinity in both ways, and now I have to start somewhere and then cover the whole thing. What?
Start at 0 and go right.
And go right, left, right, like this. So like this, that way, and so on. Okay, back and forth. Okay, so and that will give you a bijection between the integers and the natural numbers. So think about a formula. Okay, so this one is hard. That one should be manageable. A formula that you go back and forth. So certainly you remember
Natural numbers.
from natural numbers to integers. Yes. Onto.
Okay. And would it be like a cube? Would it like cube?
Cube by cube.
Like the cube of a negative number, like where it goes wait, no, I'm thinking something else. Never
You're
mind.
thinking -1.
No, yeah.
I think that's what you're thinking. That's what you're
Yeah.
going to need it in order to alternate
Yes,
between positive and negative.
yeah.
But then it has to go twice as fast. So it will alternate between. It will be like alternating between. Well, you can have you can have probably a good idea you can have a recursive formula which is just as good. So this one formula suggests that I try to do here, suggests an explicit formula in terms of n, but you could go recursive. You know what recursive is? You find the next element based on the current element. Okay, so if you know that I'm here right now, what do? So suppose this is 0. So I add 1 if the number is positive or 0, and hold on a second. I add 1. So if number is even, okay, if number is even, then I add 1. Okay, I progress this way. If the number is odd, which is this, what do? I multiply by -1. Right? So once again, n plus 1 if n is even, -n if n is odd. I think. Well, it might be. What if we are negative? I think my picture isn't quite right here. Well, it could be. What I meant here is you can progress first like this, and then make a flip, and then progress again. Well, you can do it in a number of ways. I don't think my formula still works. So think about it. Just a couple of ideas. You can try to use -1 to the n, or you can just invent pretty much like an algorithm for computing it. It's also a good exercise to take this picture in and write it as an algorithm. You can even do it with like a Excel. How do you make it go spiral? Okay. Okay. So now non-countable sets. Are there non-countable sets bigger than countable? And then there is. The reals are such an example. But before we go there, let's look at some reals, how they interact with each other. So some subset of the reals, how they interact with each other. And that's the best example in the beginning is matching an interval, a finite interval, with an infinite interval. So infinite interval being all the reals. And as you can see, that's what tangent provides. Once we switch from integers to reals, all kinds of functions from calculus will be applicable. So for integers, it's more about sequences, and once you deal with reals, it's more about just functions. However, do not assume that it will work out every time like this.
So the reals are not countable.
Right, but that's still to be demonstrated. So I want to look at the non-countable sets, subsets of the reals before just to get a feel of it. And so you hopefully, before we prove it, we convince ourselves that it must be true. Okay, so that's what I tried to do yesterday, compare integers and reals, and which might have seemed convincing yesterday, but not today, because we already know that rational numbers are really dense and they're still countable. Okay, so as you can see, so that's something that expands your mind a little by little. So, the best you can say about reals is they are also dense, but the fact that they're dense doesn't make them uncountable. So, yeah, so that will have to be demonstrated. But okay, so that's an example of a smaller set being equivalent to a set which is larger.
What does countable mean exactly? Like, you say that it's countable or not, but what...
Equivalent to the integers, or natural numbers, same thing.
I mean, what's it used for? Like, what's the classification good for? Like, if it's countable, then why does it matter if it's countable or not?
It actually matters a lot if you look at certain things in calculus. So some sets that are countable are really small. You wouldn't have to worry about it. So you can exhaust, if you study sequences, for example, you can exhaust this set if it's countable with a sequence. Okay, if it is uncountable, you cannot. Okay, so that's a different magnitude. But it's for the most part, it appears in the more advanced part of advanced calculus and real analysis, that when you go into studying functions and spaces of functions, and well, for example, so polynomials. Well, here's an example that calculus related. There are countably many power functions. Okay, so 1, x squared, x cubed, x fourth, and so on. Okay, you can form polynomials from them, okay, through linear combinations, okay, and then you form Taylor polynomials, and you form those Taylor polynomials will give you every single function, as long as it is infinitely differentiable and so on. But there are how many other functions overall? And the answer is, well, there is no way to that is an exception. That is an exception. So if you take all the polynomials, you need only countably many functions to capture all the polynomials. So you need all the power functions, countably many, and then you take a linear combination of those, and you'll get every polynomial. So once again, power functions, countably many, and then every polynomial is a linear combination of those, right? However, what if we go beyond polynomials, and it turns out that there is no such countable set of functions that will represent all the rest of the functions through linear combinations, if it makes any sense. So that's why you need limits.
Okay. But there's still limits of non-countable?
No. I was just pointing out that why do you need limits? To represent all the polynomials, you don't need limits. So all you need those power functions, combine them together, you'll get all the polynomials through nothing but linear combinations. But if you are throwing sine into this, then you cannot get sine with those only power functions, the only polynomials. The word that I'm trying to avoid is a basis. A basis of the space of polynomials is the power functions. There are countably many of them. But if you go with all functions, even though infinitely many times differentiable, there is no such thing as a countable basis. Yeah, so that's how we know that you cannot represent everything with nothing but polynomials without actual limits. Okay, so then we can only approximate everything with polynomials, but we cannot actually represent a given function as a combination of those. So how do you know that you cannot represent sine as a composition or sum of polynomials? That's how. So, and as you expand the number of functions, think about this, as you expand, and you did in calculus and before, you add more and more functions to the list, okay, and then you try to express it in terms of the old ones, which is impossible. That's why you add. So, for example, you start studying trigonometry. Suppose you already know polynomials, okay? Then you need to study trigonometry. What do? You cannot express sine as a polynomial function, so you create a sine function. Okay. You expand it. And then you start studying exponential functions. Well, wait a minute. I cannot represent the exponential functions in terms of polynomials or trigonometric functions. I can expand it further. I need the inverse. I expand to the logarithm. And so then there are other functions, it's called special functions. You keep adding them. But is there any chance you're going to stop and be done with this? And the answer is no. Because, well, for one, that process of you expanding the scope of your functions will be countable, and as you can see, that's not going to produce that is not going to give you all the functions. There are just so many of them. So even if you take functions only with that made of integers, there will be still uncountably many of them, if that makes sense. So yeah, right now we're just trying to sort it out, certain things in calculus, and Yeah, so counting numbers is the, how should I put it, simplest thing you can do with sets. So calculus is more advanced in a sense thing because there's more structure. We are not only doing counting of sets, but we also do what? We do algebra, right? So addition, subtraction. We also do limits. Before we do limits, we do measurements. Okay, so we measure distances, we measure angles, all of that can combine together in calculus, and it's totally thrown out we are not looking at that at all. We're looking at, there's a set, we just want to know how many elements there, that's it. So it's something way more simple, but also way more fundamental. So that's why it is important, so that we know that we can concentrate on one topic or one problem at a time. So that's what we do in mathematics. So counting numbers here, or counting sizes of sets, measuring angles, or measuring distances, or looking at sequences, or something else, or so we're doing limits and something like that. As far as possible, we separate one from the other so that you really extract the most important things, or things from that whole complexity. Calculus is in that sense is a pile of things, and we'll try to just sort it out and pull things gradually as you take more advanced mathematics courses. You take pieces of calculus and treat them separately. Okay, so get to the bottom of it, and this is the beginning. So set theory is unavoidable to begin with, and then and it is does not require that a lot of stuff. So modern algebra, linear algebra, topology, geometry, all of that is unnecessary. Just we're looking at every set as a bag of points. So tangent is a continuous function, and that might be misleading because it might make you think that that's how we establish the by bijections, but really it's not true because, well, as an example, let's think about well, the challenging problem is, say, 0 infinity. We looked at it just now, 0 infinity and negative infinity, so once again reals. The second set seems twice as large as the first. Okay, so can you think of a bijection? Well, from the top of my head, I can't either, but I want to point out that this is easy. If I throw it out 1 point, it's easy, right? A function from which is defined here, excluding 0, and with the image, the whole thing. So what can you think of such a function from calculus? So the graph should be one-to-one onto within this area. What's the graph? Oh, how about the logarithm? Okay, but adding an extra point makes things more complicated because the function cannot be continuous under these circumstances. So anyway, we'll continue next time.